Yeah, waiting for your order.
So for the last lecture of the day,
Yeah.
Dr. Nandakumaran.
So after so we are going to do some relaxed section. Okay, relaxation. So, all right. So I hope you have followed something in the morning. So we were trying to see the conditions when you have a minimization problem. Then the second part what we were looking is that if that functional is given by a integral functionals. That was the thing, two things we were trying to do it. And it is in a much more general setup, so it will include lot more than what you are doing it. Okay, it's a more general things. Then we also see that it's important to study minimization problems for a sequence of functionals. Okay, because the homogenization you want to see, that's what we are seeing it in the PDE is actually a derivation from the minimization problem when every conditions are set. So the more primitive objects are the minimization problems, okay, energy function. Of course, PDE can appear from other ways also, but most of the PDE which you are seeing so far are coming from the minimization problems, all these elliptic PDEs. So what I want to do before that, there is a very special case of gamma convergence, what we call it a relaxed functional, as you said, okay, and that is what essentially the gamma convergence of the sequence Fn is equal to F. So you want to know what is the limit of gamma limit of Fn, where Fn equal to F. It's not same F. So that gives you a motivation for the definition to look for. It also motivates what kind of convergence in the gamma limit you are looking, rather what axiomatic property you are looking. So the important thing is that when you are doing some generalization, you want to get the property, missed property. As I said, in normal convergence, the continuity property is lost in the process of point-wise convergence. But the uniform convergence retains that property. So again, the point-wise the important property we have seen two. One is lower semi-continuity, the other one is cohesivity. So the lower semi-continuity again will be lost in that one. So you want to recover, you want to retain, that property should be there in your limit. You don't want to lose that important thing. So then only you can, it's a kind of well-posed problem for the minimization of the limit. So before that, let me start with some examples that we will do it. So you can work out. Some example may be slightly difficult, but it is nice to work out some examples. So let's do with some examples. Okay, so I will quickly mention because I'm not sure I will reach even the definition of gamma convergence. So at least before I end, I should give the definition of gamma convergence. Right? Okay, so you have Fn is the characteristic function of minus n to n. You know characteristic function, right? It takes value 1 on that and 0 outside. That's what. What is its point-wise limit? This sequence, can you tell me? Quick will give you the definition of gamma convergence. Otherwise, we will miss gamma convergence. First. Very good. That's it. Before completing, you should give the answer, right? Point-wise. So what is infimum of Fn over R? 0, right? So what is infimum of F? So you see, even trivial problems, you don't have the convergence, right? So this infimum, that's what we are looking at it, right? For our thing, the infimum, you should get an F bar, so this is not the right EF to look for, which you have seen even in homogenization problems. That's for the kind of point-wise convergence or weak convergence, you get something. So the average convergence is not the right one. So you want to look for something for which you should get infimum of Fn equal to 1. That's the kind of thing you are looking at it. You want to identify some F naught for which infimum, and if possible, it's a set of minimizers also should converge to the set of minimizers of the limit problem. Of course, I cannot go into that much thing because you have to understand the concept of set convergence. So there are concept of Moscow convergence, AP convergence, there is a Kuratowski convergence. There are various notions of convergence of sets, and I will not even touch that. So there is one full book on Moscow convergence and AP convergence. Umberto Moscow from, I think he was from Rome, right? He was, he was in USA. I remember in the, Oh, he's there. Okay. Okay. So it's a nice book on this kind of various set convergence. A nice book. You should read such kind of books. Yes, because I read it 20 years back. I forgot. I remember green color book. I remember the books by color, not by name. Okay. So that's only a color is the only thing I stored. But this Springer books, everything comes in yellow. So I don't remember any Springer books. I know that was Pitman books by red color. So I should bring out, that's why we bought our book in a unique color. So, so that if you remember by that, you remember that book. Yeah. It's a thing. He visited long back in the 90s or something, India. All right. So that's okay. So let's take another interesting example. It's maybe little more difficult, but it's nice to compute its derivative, etc. One of the derivative computation is little difficult. I quickly tried to do it yesterday night, but I didn't get it. But so I leave it as an exercise. Okay, I think little because I had to compute some integral. I forgot integral many years back to compute. Okay, but let me write it. So you are defining fn of xi. You can do it, I think. 2 plus sin nx. Please do it not now, later you can do it. And then you can have f of xi is equal to 2 mod psi square. Okay. You understand this is x over epsilon. This is the same homogeneous, that part, oscillating function. So when n tends to infinity, this will not converge. So there is not even a point-wise convergence. But then you have a weak convergence in the appropriate places. So you have a weak convergence. So you can say that this weak limit is this way, whatever it is. Okay. So you have some weak convergence here, only weak convergence. And this is the typical situations you may face. So that's what I'm saying. So I want to compute its corresponding FNU. FNU is equal to integral of, this your domain is 0 to 1. It's a one dimension, so you can do the computation. 2 sin nx into mod u prime square. This is something like du square. Okay. That's an example of du. So you are writing like du square there. And your f of u is equal to 0 to 1 2 mod u prime square. So you try to write down its Euler equations and all that. So try to compute its derivatives. Okay. And you can, with all that, this part is easy. This part little more integration. That's what I didn't complete the computation. But after using that, you can prove that infimum of f of v over v is equal to 2. But infimum of fn of v over v, see, even though this weak convergence, this contributes. That's what you see in homogenizations, right? It's not just 2 of v. It is not 2, it is actually root 3. Okay. So you see. So this infimum of fnv do not converge to that is even infimum. Right. And so the correct functional could be, we don't know. This is a guess, right? The correct functional may be root 3 into, say, f not equal to root 3 into integral of 0 to 1 u prime square. Looks reasonable. So the one we have to identify is this, and that's not this one. Okay, that's all right. All right. One more example. That's a nice example, which you can do it. This is fn of x. It's nice to play with this. So if you want to have that kind of analysis thing, try to play with examples, not just studying theorems and proofs. That's the only way to learn maths. And all the functions, everything should be there in your fingertips. Kind of nice thing. And when you do it here, you should the figure should run through your mind. Okay, so that will come only by working out all possible examples, sketching it and all that. So it's a nice thing to sketch this. So you have fn of x is equal to e power nx into e power 2n square x square. Can you tell me its point-wise limit? As n tends to infinity, quick. You know how many of you can prove that? Because there is a term n tends to infinity, there is a term which goes to 0, right? So it's an indeterminate form. So I hope you are all learned, but your answer is correct. Okay, so that's the point-wise limit. So can you sketch that graph? That's what I say, you should sketch it. So try to understand that graph. You can do analysis later, but you should also, as I said, you should have a feeling. So I'm fixing n. I'm trying to plot fn for fix n. Okay, for a particular n, I want to plot it. What is its value at the origin? Value at the origin is 0. So n is fixed. Now you want to know x tends to infinity. X tends to infinity, what it would be? 0, right? Because it's 0 happening because exponential dominates the polynomials. That's all statement, but you have to prove it exponential. When you multiply a polynomial with a small exponential term, it will kill the polynomial. Okay, which requires an analysis proof. If you are not done, please do it. These are all things which will make your homogeneous, any subject better. Okay, so yes, so for a particular n, as x tends to infinity, and this is a positive quantity for x positive, it's an odd function. Okay, so it will be positive, but it goes to infinity. You can check that there is and hence there will be a maximum or minimum, but it doesn't get oscillate because there is no oscillatory phenomena here. You are not going to get any oscillation. That's all. By working, you will get that feeling. So it won't get oscillations that easily. Okay, so you can check that there is only one maximum. So it will go like this. And then it's an odd function. So it will go exactly like this. And this will happen exactly at the same place. Okay. So what it would be happen, now we are trying to understand this. This is going to, where does it go? Okay. So what would be the infimum of Fn? You want to compute, right? And infimum of Fn happens here, not here. And you can compute that point. That's easy to compute. So let me write this happens at 1 by 2n. This is minus 1 by 2n. And interestingly, this value is independent of, that is what it makes this example interesting. This is 1 by 2 root e. So for every n, the maximum and minimum values are fixed. That's not changing. Now you see this is a kind of pulling happening, right? This is also minus 1 by 2 root e. Which you can do it. You differentiate and find the minimum and maximum values, evaluate it and you get it. That's not a point. So what is infimum of Fn? Minus 1 by 2 root e. It does not change. So when n tends to infinity now, what will happen? When n tends to infinity, this is also 2n. N tends to infinity, these points move in this close, but this will not go. So there will be a high gradient coming into picture. So as n tends to infinity, this moves, but this moves without changing. It shifts only. Okay, so the next function will be again like this, with the same minimum. Okay, so it goes there. Okay, so the minimum you will get it, so the minimum of f is 0, you already got it. Okay, but here when you pull it, the minimum retains there at minus 1 by 2 root e. And this we want to recover in our limit function. That's what, so these are all simple one-dimensional function. Then you can see that you are doing the analysis in the other function spaces where solutions are coming from PDE, etc. And you won't have this kind of pictorial definition. So you want to, so you prefer your function, how does this function now look like? You definitely you want, so you can't put something arbitrary also. Okay, you want to retain all the, if everything is nice, it is nice. So that's why you do little more analysis. So if you do it, this should have a minimum this, that is for sure. Then only infimum of Fn will converge just to that. But other points also you have to be careful. But then using this, you can analyze little more. If you take any neighborhood here, on this portion and this portion, you can see some sort of uniform convergence. Okay, so it will have the kind of uniformity converging. That means for every outside, as a neighborhood of the origin, you will get uniform convergence. So hence uniformly converge, so that's a good convergence, you don't want to miss that, right? So your function value has to be 0 outside that. So that intuitively tells you that, these are all intuitive feeling which you want to do it. It immediately tells you that if this is has to be 0, and at 0, it has to be this one. And this is the function exactly we have to look for, we have to get through the gamma convergence, which you are missing. Okay. After introducing, you can verify that indeed that is the gamma limit later. Okay. In fact, you can now that's why you have to construct the examples in such a way that it will provide you, the idea should provide you a family of examples, a plenty of examples, if possible. Okay, complicated things you may get one example, but you should construct in such a way. So from this, it doesn't matter, I didn't give the function definition, right? That shows that I need only the behavior like that. So you can construct an infinitely many if you want. I can have something like this, I don't change here. You can have very simple construction so that this is fixed and this is changing. It will have the same phenomena. And I can do that as much as I like it. And so I can have any kind of, you can have a family of functions which will provide you different gamma limits, infimum. I can put it anything, right? I can put this way. And I can do this, it's the same thing. It will shift, you keep this fixed. That will, in the neighborhood, you will lose that uniform convergence. Okay. But you get, by doing this, I still get the point-wise convergence, you see? But the uniform convergence you lost. Okay. Now let me go to the other notion, relaxation, which will provide me more or less the definition. So it's a different concept already. Morning I told you I want to give you the various concepts and various terminologies. As itself is a very independent full subject which you can pursue your entire. Okay. So it's not just for the homogenization sake I'm introducing this. This another subject is nice to learn when you do something else. All right. So the idea is that when you have an infimum thing, idea of relaxation, this may not have the kind of property of lower semi-continuity, okay? And hence this may not have a solution. So the basic idea is you want to replace this by another function, so that this will become a minimum point. So the minimum point, so you want to see that have a solution, and it gives you everything basically of this one, except that it may not have a solution, but then you want to retain its all minimizing sequences should be a minimizing sequences here and there, and then this will have a minimum solution. Okay, that means your F bar should be, from the morning discussion, you realize that F bar should be the one which has the lower semi-continuity. F may not have that property. So you are trying to relaxing that function. Okay? So there's a nice way of defining, that's one basic idea of relaxation. And this is exactly the property in the gamma limit we are looking for. So we have a gamma limit, and the Fn's may have a lower semi-continuity, or may not have the lower semi-continuity. Both are fine. If Fn doesn't have lower semi-continuity, you can relax it to get that lower semi-continuity. So that will infimum will become a minimum, and the minimization sequence essentially you'll get it both sides. And then even if you have lower semi-continuity, the limit if you do not have the lower semi-continuity, in the limit we want the lower semi-continuity. So it's a very special case of the gamma convergence, where Fn is replaced by F. So all these properties should be here, and then we will just take that property and define it for your gamma convergence for the sequence. That's what we are going to do it. And the definition of relaxed function is quite easy. Okay, we'll write a theorem anyway. So what you do is that, so given F, you construct the set of all semi-continuous function. So going to define a semi-continuous envelope. It's something like an envelope. Okay, is the set of all G functions. G is lower semi-continuous and G less than or equal to F. So looking for all the lower semi-continuous functions less than or equal to F, and looking the biggest one possible, which is the nearest one possible to F. So you are, in other words, you are looking for the largest lower semi-continuous function less than or equal to F. So that's it. Okay, so define, this is the definition. F bar of Y is equal to supremum of G in G of F is equal to G of Y. Yes, G of F. That's the definition. So how do you know that? First of all, that is lower semi-continuous, right? So there is a nice proposition which you can prove it. You can sit at home and do it. You don't have to see everything through the book to prove it. Small things you try to prove it, it may take a day. If you see the book, it may take few seconds, but if you do it yourself, take a day, but it's worth doing it during student time when you have it. Because process, you will learn many things which you can do it later. First. So many things you can learn in the process, right? So there's a proposition in the lower semi-continuous. Arbitrary supremum of lower semi-continuous functions is lower semi-continuous. So you take a family of lower semi-continuous functions and then take its supremum. Okay, which is lower semi-continuous. But arbitrary infimum is not. Okay, finite infimum of lower semi-continuous functions is lower semi-continuous, but need not be arbitrary infimum. Do you understand that statement? I didn't write it. That you can understand, right? If you have a family of lower semi-continuous, take the supremum function. You know the supremum function, right? Supremum of f for g of x for all x, or for all g. Okay, and if you take finite, yes. Okay, again you can have a family of, you can cook up from the morning examples. So that's why if you understood the morning examples, where you have a lower semi-continuous function, if you have a discontinuity, if you have put the value upstairs, you don't get it, right? You recall that. Whenever you have a function where you have a discontinuity in the convex function, I remove that point, I put the point up. Then you don't have a lower semi-continuous. So you take a family in such a way that its supremum is that function. That's easy, right? Do you recall? So suppose I take a function like this, and then I take another function like this. And again I will keep it here. So I construct move, but this point it touches. So I'm coming, these are my a collection of GI. These are all continuous functions and hence it is lower semi-continuous. Yeah, probably I not told that. A function is continuous if and only if it's both lower semi-continuous and upper semi-continuous, okay? So a very continuous function is lower semi-continuous. All GIs are lower semi-continuous. So what is its infimum? Can you tell me? Infimum of GI, which is that function? Can you tell me? What is g of x? Yeah, only at x equal to 0, g of 0 is equal to 1, say, this is 1, right? So gi of 0 is equal to 1 for every 0. So its infimum is 0. For all other points, there will be functions which will become 0. So at x equal to 0, and it is 1, x not equal to 0. So this is a function. You have this function 1. You see, that function is not lower semi-continuous. Anything which is discontinuity up, it cannot be lower semi-continuous, because if you take neighborhoods, this neighborhood will not go above that. Okay. So it's not just the definitions are important for the paper, but it is how you grasp your definitions are more important. So definitions don't come from the sky one day. Okay, definitions are imposed looking at our necessities, right? You call it from the examples and other things. Okay, so you have this infimum, but it is the other way for upper semi-continuous functions. Okay, upper semi-continuous arbitrary infimum is upper semi-continuous, and finite union is finite supremum is upper semi-continuous. So it's everything changes because you can just replace f by minus f and get all the results. Okay, all right. Yeah, hence this is lower semi-continuous. If GS are lower semi-continuous, because it's a supremum over G, hence f bar is lower semi-continuous. F bar is lower semi-continuous. And f bar is less than or equal to f. And f bar is called the relaxed function. F bar is called the relaxed function. Okay. There are, of course, that definition of f bar is not in a really computable form. So there are many other which you can prove it, which I don't want to do it. There are other, so it's this is not just directly, again, this may not be the first thought process. Okay, the first thought process is something different, but that process is intuition is difficult to get it. So hopefully this may be, I think, it's a more general definition. So it is a result. You can, probably this is more computable, because there you have to find out all the lower semi-continuous functions. But this is, so if something is computing based on some other candidate, that will always be not the right definite thing. Okay, you should always have something computable in terms of the given one. The one given to you is only f. So we should have as much as possible equivalent characterization in terms of the given data. Okay, so there you have data G, which you are constructed using, that's more difficult. So what you do is that, so if you have any point x here, you look at all possible neighborhoods and do an inf-sup process. So this is what u in n of x is the definition. You can take this as the definition if you want. Okay. Inf of u of y, f of y, where y is in u. So what you do is that you look at a neighborhood, minimize it, and take the supremum over all possible things. So you can prove it. There are a few more results which I don't want to discuss it here, but I want to state one important characterization. That is what it makes your gamma convergence, because we have only limited time. So okay, so already half an hour. Right. So, so let's look at an equivalent characterization All can be proved without much difficulty, but as I said, each one needs some time to prove it. So that's not in the first lecture, it doesn't matter. In the beginning, first time you are hearing. And in any case, proofs you have to sit back home and study. Okay, proofs can't be really learned from the classroom. Okay, you may understand the proof, but then by the time the class is over, you may also forget it equally. Okay, unless you eventually work out. Okay, so f bar is the relaxed functional if and only if relaxed functional if and only if two things happens. So this is another characterization of that one. Okay. For all, read this. This is going to be your gamma convergent definition with a slight modification. Okay. This characterization is what it brings the definition. Of course, there is a characterization in this way also. That's what I say, more abstract form in a general topological space. This can be done there. Nx is the collection of all neighborhoods. Okay. You take any neighborhood, invite many things, and take the supremum for all possible neighborhoods. For all x in X, and for all xn converges to X, that means you take any X, take any arbitrary, this is arbitrary, any sequence xn convergence to X, with respect to topology you are working. If you are working with weak topology, you have to do everything with weak topology, so it will be difficult. This is something like a weak lower semi, all bad definitions will come. So whatever be the topology, if you are working with weak topology, everything convergence is with respect to that topology. So right now we have an extreme matrix space X as a topology. We are not doing it. Should satisfy f of x, f bar of x. This is exactly somewhat the lower semi-continuous definition. But f need not be lower semi-continuous, so you are imposing it on that f bar in terms of f. That's all you are doing it. So if you really debug the definition, you can see that yes, it is easily. So outside it is masked by the big program. But when you go and see each line of the program, you see that it's natural. Okay. This should be lower limit of f of xn. So if f happen to be the if I happen to be lower semi-continuous, you get this for f bar. Okay, so you want if f bar is a relaxed function, this is one condition. The second condition is, this is one condition, this is the second condition is, for all x in X, so every sequence, this should be lower than that, but you want for at least one sequence, equality is achieved. Okay, for every sequence you have that inequality, and for some sequence, for one sequence, you should have the equality. So in all our process of test functions, constructions, everything is essentially is a construction of that sequence, the second condition. You want to, and that may not be for arbitrary things, it may not happen for arbitrary things. You have to cleverly choose that sequence. The first one is a direct proof. You take arbitrary x and convert. The second one, for all x, there x is. So this is a kind of, you have to construct cleverly if you want to do it in general. There x is xn, which converges to x, such that f bar of x should be the limit, which is equivalent to saying the upper limit of f of xn, right? It's enough to write upper limit here, because, so of course, 2 is equivalent to, in view of 1, 2 is equivalent to 2 prime, where x is xn, converges to x, such that f bar of x is equal to limit of f of xn. Is this clear to you? Because f bar of x. Because if there is a sequence converging to that, f bar will be greater than upper limit, greater than lower limit, greater than f bar of x, and you get that equality, right? Upper limit will be greater than or equal to lower limit, that is greater than or equal to f bar of x, so you get equality, okay? F bar of x equal to f bar of x, you get it, So you have this one. So this means that the lower limit criteria should be satisfied, and for one sequence, so everything is less than, that's not enough. And you also seen that it is achieved. So you are using the best one. You see that you have a F there, you are trying to look for an F thing, but then something achieving below that is not enough. One sequence tells you that you can go up to that sequence. Otherwise, once you may have, if you don't have the second condition, you may be able to construct many. That's not what you want it. You want that precise one. And constructing this sequence in applications will always be an issue. And that will be the major issue of doing that. Okay, you are trying to choose the best test functions available. Okay, so that is what the F bar is, the relaxed functional. And then, yes. Yeah, as I said, gamma convergence is motivated by this one. F bar is already this one, is lower semi-continuous. So you're looking for a gamma limit for which this F, instead of F, now you have a sequence. You demand these two conditions where F is replaced by Fn. Okay, then you call it a gamma limit. So your definition is there in front of you, which you yourself can rewrite now. So that's what I said, by the middle of, you have your definition. Will come to you. You don't have to look for it. But I want to go. Yeah, I want to connect it with this, your continuity definition. What the continuity definition tells you, so some comparison with continuity. Just like we will do for gamma comparison with the continuity of F. What is continuity of F tells you? For every sequence xn converges to x, f of xn converges to f of x. But I can rewrite that as a two definitions, right? What does tell you? The continuity of tells you that there are two conditions, right? I'm writing that one. For all x and for all xn converges to x, my f of x should be less than or equal to lower limit of fn of x, f of xn, and b, both should satisfy for all x and for all xn converges to x. Here, keep that in mind. Okay, f of x greater than or equal to upper limit of f of x. That's the continuity definition, right? Because if these both are satisfied, then f of x is less than or equal to this, less than or equal to this, less than or equal to f of x. So you have f of x equal to limit of f of x. So the continuity definition can be rewritten in this way. Now I want to compare these two. So it's not compare, but you can see that it's a kind of modification of this one. Let's look at the first one. So you cannot say this implies that or that implies this. So look at here, what it tells you here, really. What is this happening? For all x and for all xn, probably not at this stage, because I'm not able to do anything. Okay, maybe after the gamma convergence. So let's keep that. Okay, it doesn't say anything. It's not giving any information right now. It's giving some information, but that's not the information I want it. I will do it at the gamma convergence level. Let's, since we don't have enough time, so let's keep that there. Okay. So let me write the theorem without proof. This is the theorem now. Okay. Let f from x to r bar be cohesive. See, this is an interesting thing. F bar is not telling anything about cohesivity. So it gained lower semi-continuity without losing coercivity. That's what this theorem and more it tells you. So in the process, your coercivity property is not lost because we are looking at the same minimizing sequences. Okay, so then F bar is A is lower semi-continuous and coercive, and further you know that. So F bar is lower semi-continuous and coercive. It has a minimal solution by the morning argument. Right? The theorem which we have stated about the coercivity and lower semi-continuous. And minimum, this exists now because of the coercivity and thing. It will exist, minimum exists for an infimum point. And what it tells that this is same as, so you are not losing. You are not, because this may not have the solution because of lower semi-continuity, but this will tell you the same minimizing sequences. Y is in X. Okay. And B, there is an equivalence. Every cluster point, every limit point of a minimizing sequence of F is a minimum point. So if you have minimizing sequence here, and its limit point will be the solution here. Okay, that is the one. It cannot achieve here. It may not achieve because we don't know for F the infimum is achieved. So if you take a minimizing sequence here, even if it converges, it may not convert. That's what we have seen it. But it says that it will go to the minimum point because this is a minimum point. Okay, is a minimum point of that's basically the general relaxed function F bar. And C, this is a similar, almost a similar thing. Conversely, converse is also true. So this is the best function, best lower semi-continuous function you can look for it. And every minimum point of F is the limit of a minimizing sequence. Is the limit of a minimizing sequence of F. So that gives you the complete picture about in the relaxed functional. So you don't have a solution. This one. Ah, of course. Thank you. It has to be. So you see, to have that. So the minimum points of this is the values is equal, and the minimum point where it can be come from the, that is what is available to you. It should be, because this is the data for you. Okay, so it's a minimizing sequence from here, which you can construct for your problem. Okay, so it will be the kind, that's what it's called, that's the relaxed one. So it's a both way it is giving. You can, but it may not, that sequence may not satisfy that one. So it's a relaxing basically. It can take it, but it may not be there because there is no continuity. That's the whole thing.
One sequence doing that.
One sequence doing that.
So if constant sequence does it, it's fine.
It is very good.
If it doesn't do it, then
That is where the problem. Okay. Yeah, if you take what will happen, but this inequality may not be there. If I replace f of xn, the upper limit of that may not be this one. This inequality may not be satisfied with xn equal to x. So it's a weaker condition, I'm going to say that. If you have, yes, that is the point I want to tell, but I will do the limit. That's exactly what you are doing. Yes, that is what I'm saying. F bar is
the second condition, you are getting
you don't get it. How do you get it?
that's even not a criteria.
True, but this is not F bar. This is F. Yes, for F bar you have it. This is F. given data. Is that okay? It's not trivial. In fact, this is the difficult part of your whole theory. If lower semi-continuous, no problem, F bar equal to F.
Yeah, so then the second part,
Then you don't have to do anything. Then it is a limit. Yes, F base is continuous. Yes, that's true. If it's a lower semi-continuous, no problem. The whole issue is F is not lower semi-continuous, right? You are interested in that aspect. Yeah, you can think of it. Anything is there, you can ask me again. Yes, if F is lower semi-continuous, then F bar equal to F. But then it will be limit because of the condition 1. This I have written in this way. This is actually equality for the limit. No, we are not taking arbitrary lower semi-continuous. F is general functional.
In the case when F is F bar, you can actually take x and equal to x.
Yes, is that what you are asking?
Which is what I'm saying, that for any given x, x and equal to x can work, may work.
It may work.
It may not work always.
Always.
In that case, you need to find
And in fact, I am telling that's the most difficult part in this relaxed functional and the gamma convergence. Okay, that's the point. You have to cook up the right functional. Okay, so if you have F nice property, there's no problem. All things are fine. Okay, you don't. Okay, yeah, it will take some time. Yeah, doubts are good. Anyway, let's not spend too much time. We can discuss it. Let me see whether I have some example. Yeah. Okay, I'll quickly tell you some results in relaxed functionals, and that's and then I will give you the definition of gamma convergence. We are almost there. Definition of gamma convergence is the same, where F will be replaced by the Fn. Okay, but let's do what we are looking in gamma convergence in the context of relaxed functionals. And what are the analysis result, the major result available in the convex analysis, in the relaxed functional setup, and especially the representation of the relaxed integral. Okay, you will see that it's not that trivial. Okay, so you take up this, assume the conditions which you know. I don't want to write the same conditions F, which has growth conditions like P and T. So you will have a lower growth condition, you have an upper growth condition. All that, with this I'm interested in so you have one function from two functions, LP to R bar, and G from W1P to R bar. And suppose I define F of U, I want to see F of U in the as a functional in LP, so same thing more or less, but one I will see in the LP topology, the other one I will see in W1P topology. Okay, so this is F of U is equal to integral of F of x du of x if U is in W1P, okay, and plus infinity if U is in LP minus W1P. So I am viewing my F as a functional in LP. So that's what you are trying to do it. Okay, so basically you are doing minimization, but with respect to LP topology. Okay, and then your GU, I am just defining integral of F of x du of x, and it is defined only here. Yeah, G. Yeah, you can put G, but doesn't matter. Same if I'm not going to do the problem now, right? I'm not going to write the minimization of integral grade. I just want to know this, if you consider this as a function in the LP topology in this fashion, if this what are its corresponding? So it's an integral functionals. As I said that it will have the relaxed functional. So my fundamental and difficult question which I told you in the morning, I want to have the representation of that limit relaxed functional in terms of the integral functional. There are some, it's nice theory. It's better to, I'm introducing that so you can probably read something in your leisure time or if you want to learn something more or read some convex analysis book. So this is given by defining what are called the some sort of a convexification of the given function. It's called, some places you call it Legendre transformation, probably you have. Here, probably I call it first polar. So given f is a two variable function. So you call it the first polar function. You are looking for the best convex approximation, okay, which we denoted by f star of x theta. So theta is basically a dual variable in applications, but in Rn you don't see that, but it's actually the dual of Rn is Rn, so theta is taken to be its dual, okay. It's a kind of, you are approximating something. You know that in the normal things, convex functions can be taken as envelope of your affine planes, right? You know that such kind of things you should see this in a more generality. Instead of writing a convex function y equal to x square or any function, I can say that it is the envelope of a family of one parameter family of the tangent lines or any other kind of things. So these are the ideas which developed it. So looking for all affine transformations. So this is your affine transformation, theta minus f of x theta, because this is fixed now, xi. Okay. You define, and then from there you can define your second polar. Yeah, this may not give you much idea, but why I am stating here, where in case he writes tomorrow about the integral representations for the thing, you can see that in a very special case how the integral representations looks like. And then you can, in that special case, your integral, what is your integral? Because you want to write your f bar in terms of your integral. Okay, what is the relaxed function? You know that relaxed functional exists, but you want to write your relaxed functional in a similar form. That's what you are trying to do it in the last few days for the homogenization problem. Okay, the second polar is the first polar of f star. So it is compact to the base space again. So you will define f double star of xi in a similar way. So you do this one. Supremum of now theta of again psi theta minus f star of x theta. Okay. All right. And the interesting, what is the results which I am not even going to write, you will start with certain estimates here, lower and upper estimates. Similar estimates you can prove for this kind of things. Okay, so you will get similar lower bound and upper bound. So you have certain bounds from the lower side, you have certain bounds, something like mod psi power p and other side also mod. It's a kind of growth rate of mod psi power p. And similar growth rate with different constants can be proved for that one. This is a bit hard, so you don't immediately try to attempt. I'm telling that how, this is just to show you that the integral representation is a very delicate process, okay, which I hope he will do it, something you will see, okay. So then I want to tell you what is my f bar of u. You see, it's not just that. F bar of u is integral f double star of, this is the one it is coming, okay. F star of u, x du of x and plus infinity. This is when it is in W1P, otherwise, and g bar of u, same thing, integral of f double star of u. So you see, you have a correct representation of that. So you can write that you are relaxed, so the relaxed function, so you want to study the minimization of this one, you have to take its Legendre type of by second polar and study the minimization problem of that, which has a unique solution. So once you have that solution, that will be a kind of approximation that means, because the same minimizing sequences approximate. That's what this theorem tells you. So you want to get you don't have an exact solution, but then you have a minimizing sequence. Okay, and that minimizing sequence will go to the minimum thing. So you have something closer to it. So you basically study that problem. That's what you do it in homogenization also. Okay. Okay, so let me give you before ending another 10 minutes or so. The definition, which we are waiting, right? At least I am waiting so that I can finish the talk. Okay, all right. That's the definition of gamma convergence. So Fn, let Fn, F naught from X to R be given functionals then we say Fn converges to gamma converges, I just put this notation, gamma converges to F naught, or you can say that F naught is equal to gamma limit of Fn if a similar condition satisfies exactly that conditions of relaxation. And for all x in x, for all xn converges to x, F naught of x is less than or equal to lower limit of Fn of xn. So that's all, just replaced f by Fn. 2, for all x in x, there x is xn converges to x such that F naught of x, either upper limit or you can just say that limit. By the argument, it is the same limit of Fn of x. So you need one sequence where the limit is achieved. For all other points, you have this. Okay. That is what the gamma limit. Yeah, here I want to do the comparison. So I want to do, now the comparison is, I want to do the comparison with the point-wise convergence. Comparison with the point-wise convergence. What is the comparison? What is the meaning of Fn converges to F point-wise? Fn converges to F point-wise. What is the meaning? I can write it as an if and only if statement in which for all x and for all xn converges to x, f of x should be less than or equal to lower. Meaning means fnx converges to fx. In other words, the f of x should be limit of f of x, right? Fn of x, right? No, sorry. What? This is not there. This is not there. Okay. For all x, Fn of x, that's why I made a mistake. Not mistake, I couldn't interpret properly. This should happen. And B, for all x, f of x should be greater than or equal to upper limit of Fn of x. Right? This is the equivalent meaning of Fnx converges to f of x. Because for all x, this is greater than, which is greater than or equal to this one, which is greater than or equal to f of x. So you have f of x equal to the limit x's and limit of f. Now try to compare my a and t, and maybe it's an answer for you. Your doubts, if at all something. Look at here. What this has to happen then? This inequality should happen for x, right? X is fixed. What does it say is that this inequality should happen not only for xn equal to x, it should happen for every xn converges to x. So even if you have something, so it's a kind of double thing. As n varying, fn varying, xn also varying. Just like we have seen that. Yeah, that's what I keep on repeating. I repeated 5 times. This is the 6th time by you. It's true. The most first part comes generally gets it. This is the, as he says, this is the difficult part because you have to construct that one. Yeah, I will come to that. So this is actually this is the part to get it because this you have to construct it. So this is what to straightforward for thing. You don't have that. So you look here, you understood. So which is weaker, A or weaker? A is weaker than 1. Do you understand that? Because 1 has to happen for every sequence. And A has to happen only for one sequence. So there you have to happen only for the particular sequence xn equal to A. Of course, x, as he says, xn equal to x is a sequence. So this has to happen not only for xn equal to x, it has to happen for every other things which converging. But here meaning only that one sequence it has to happen. What about these two? Now look at here, for x in x, you have to prove only one sequence existing for which this inequality is true. But what does this tells you that? It tells you that it has to happen precisely for the sequence xn equal to x. You see the difference? And in 2, it is enough to happen for some sequence, but in B, it has to happen for that particular sequence xn equal to x. So you don't have the freedom. So that way, so you cannot have this implies this or this implies that. Okay, but then this is another motivation if you want the definition. I'm actually relaxing this definition, actually strengthening this definition, relaxing this definition in the gamma convergence. So B is stronger than 2. So we are not fully understood. Please think for some time. Not think for some time, go and study. That time it will take. And lecture to somebody else, that's the best way to teach. Okay, study and bore your, first you start doing it with your colleagues or friends, and then when you get an opportunity, trouble your audience, right? Just I do it, or rather we do it, keep on doing it. All right. So you have your gamma convergence definition. What do I want to do further? I should stop, that's what you are expecting, right? Yeah, I will do that one. So let me recall these examples now. And so this is a now exercise now for you. If you choose this example, fx equal to nx e power minus n square x square, right? That's the example, right? 2. 2 is not must, but you can get some other constant. And what did we see? We saw this point wise limit is 0. Then we saw that it's a minimum achieved at half of e power minus half square. So its gamma limit is exactly that function. Now you have to prove it. Okay, you try to prove that one. It's interesting because it's all straightforward and easy thing. So it would be nice to construct it. Give a proof. It's a very nice proof. So you will understand that functions in a way. It's a delicate proof, but only one line proof. You have to understand it. Okay, I already explained to you when n tends to infinity it moves, but the minimum value does not move. It will go straight. Okay, so it comes like that. So you pick up that sequence and do the example. So only you have to worry about the origin. All other points are uniform, which I already give you. So you write down the complete proof. If x is different from 0, what happens? When x is equal to 0, what happens? Because if x is different from 0, any sequence converging will be bounded away. That's what will happen. Suppose you have x different from 0, and xn converges to x. That xn, right? It will go, if x is 0 here, if x is here, and xn converges to x, it will eventually come here. When you eventually come here, the problem comes when this and this get cancels. When this and this get cancels, what will happen? The exponential smallness will be lost. We try to kill this, by using the smallness of the exponential term. Decaying, exponential decay is used to kill the polynomial decay. But when x is far away from x, write down mathematically, the sequence converging to x will be away from the boundary, away from the origin. Hence, this cannot kill this large because this can be killed only when this is go to 0. But it's move away from that. That means you will have an exponential term will be retained there. You won't lose your exponential term. Small decaying exponential term will not be decayed. Hence, every x not equal to 0, it will go to 0. So your both conditions will be automatically satisfied. On the other hand, when x equal to 0, we already seen that example. Okay? When x equal to 0, what will happen is that if I choose, say 1 over n, when I choose x equal to 1 over n, this and this will get cancelled, and you see x equal to 1 over n and n cancel, you are getting a sequence e power minus 2, you see. So it is not going to 0. So there are sequences which will not go to 0. But then you construct a sequence that way and prove that the gamma limit. I given almost all the proof that only thing you have to write it. 0 if x not equal to 0 minus half of, I think, e power minus r. It's nice. You don't need any gamma convergence, you don't need homogenization theory, you don't need PDE to prove this. You only need your basic analysis, which I am sure all of you have done it, right? During your graduation. What happened to another example? I will soon stop it. Fn of x is equal to sin nx. Can you tell me its gamma limit? By intuition? By intuition? What would be the minimum of f of fn? You have some intuition. What is infimum of fn? Minus 1, right? So whatever subsequential take limit, it will be between minus 1 and 1. So naturally you expect everything to go to minus 1, right? So you can, and if your n becomes oscillating faster and faster, the lower humps will go any point you like it, you know that, right? Any point can be achieved there by subsequential. You know that sin nx, right? When sin nx oscillates faster and faster, you can always construct sequences reaching any number you choose between minus 1 and 1. Do you see that? Correct? It oscillates faster. So you can choose the correct thing, so you get that value. Okay, so any point, anywhere. So what would be your gamma limit? Minus 1, identically. So you see, you have done it, right? Its gamma limit is f naught, identically 1, minus 1. Because the lower limit is. Anything else? And I think I will stop it soon, right? You are tired, right? So there is a theorem now. Okay, the next page is about the theorem. It's here in my book, which is written. It tells you what? It tells you that minimum of f naught is coercive, all that assumptions. Eventually, this is what you are looking at it, right? Will be limit of infimum of or minimum. So you assume under some conditions, infimum or minimum. If you are doing the minimization over a compact set, you have minimum is achieved. So there are other results. Instead of x, if you take a compact set, the minimum can achieve there, and then all this can be replaced. So basically, you have a result like this. That's what you are looking at it. Now you have your Fn in the homogenization, f of x over epsilon, and its infimum value is nothing but your solution to your PDE, and then you have an f naught thing. As I said, the final nail or final difficult thing, if Fn is given by an integral functional, is f given by an integral functional? As I said, that is extremely hard to understand. You have to understand some, all these gamma limits depends on the domain you study. So you have to understand the gamma limit not just as a function of x, it has to understand its behavior with respect to the domain. That's a crucial point. That's a crucial point actually. So when you have a gamma limit, it not only depends on your u, and it actually be hidden because our domain is fixed. So now you choose all the open sets or all the open sets in Rn. So for each open set, you will be able to deduce a gamma limit. Of course, that's also a delicate thing, so you may need some topological second countability axiom, all that. Let's not bother about that. Assuming that, so your gamma limit will also depend on A. So far A is equal to omega is fixed. And you have to understand it as a set function. Okay, so not only you have to understand the behavior of f naught as u, you have to also understand the behavior as A. You have seen in your one of the courses in measure theory, the moment you are trying to understand it as a set function, you will see the measure property. So you have to get, first you have to prove, so the idea of integral representation is to give something axiomatically. Forget about all the limit of a gamma limit or something. Suppose you have a set function. For every u, you have a set function defined. And can you give me a set of axioms so that my functional is an integral? That is what, when you set an axiom, means you try to give some set of axioms, 4 to 5 axioms. If my f satisfies all these set axioms, then you can prove that. And one of the crucial part is proving certain, that has to be a border measure coming from that. So you have to prove some very delicate estimates called the fundamental estimate for f naught using the property static. So proving that is the crucial thing, and you will see something tomorrow from Harsha, right? Yeah. Okay. Simple, even one-dimensional example is difficult. Then you say that we have learned so many block wave method nicely, unfolding method. Why do you want gamma convergence? That's for debate during your travel, not with me. Okay, so it's okay then. Right, stop.